Should I go back and do them again? My apologies to those viewing this video. We've already gone through problem 1 and problem 17 in chapters, both in chapter 3. Those are the only ones giving you trouble? Okay. Well, let's see.
29.
I'm sorry, 29?
Yeah.
29. Chapter 3, 29. Okay. Okay, let's see what we're given for 29. A 2.8 gram sample of an oxide of bromine. So we got bromine, and we've got so many bromines and so many oxides together. That's all we can say at this point, an oxide of bromine. And we have 2.80 grams of that, and that is converted to silver bromide by some reaction. We don't know what the reaction is, but we're going to make it into silver bromide, and when we do that, we get 4.698 grams. What we want to know is the empirical formula here. What is N? What is M? Okay. And we're given the molar mass of this one just in case we need it. This is silver bromide. Okay. All right, we're not given the stoichiometry of the problem. We don't know if there are any coefficients here. So we're going to have to work from the mass numbers and the formulas that were given. So if we have 4.698 grams of silver bromide, I'm thinking the best way to approach this is how many moles of bromide does that represent? Because it's the same moles of bromine there as it is here. Okay. So if we convert this to silver bromide, moles of bromide, we'll put this one on the bottom, grams here. There. Okay, and we need a calculator. 4.698, 187.2. So this is 2.50 times 10 to the minus 2 moles of silver bromide. And since the compound is 1:1, that's also the moles of bromine, right? Because it's 1:1 ratio, 1:1. So this is also 2.50 times 10 to the minus 2 moles of bromine. Okay, yeah.
The 187.78 isn't, that's the molar mass of the entire compound.
Yes.
Right. So,
Yes. Right. And this is the mass of the entire compound. So we had to use this value first to give us moles of silver bromide. because this cancels. Leaves us with moles.
Would you not have to divide wouldn't it be half of the molar mass of the compound to get bromide by itself?
Uh-uh.
So,
Well, this calculation, I mean, suppose we didn't care. I mean, suppose the question was, if you have this mass of silver bromide, how many moles do you have? It's just that conversion. This is how many moles of silver bromide you have. Then we use the ratio. There's one bromine for every mole of silver bromide. It's one to one, right? Then we can say, if it's this many moles of that, it's also that many moles of this. So, what mass does this represent? That's the next question. Because we do have total mass over here. So part of this mass is bromine. And we know that all these bromines came from here. All those bromines came from here. So, and we can't create or destroy mass. So the mass is the same on both sides. Now that we know moles of bromine over here, we can convert it to mass of bromine over here. So we just go backwards. Moles on the bottom, grams on the top. And we need a molar mass for bromine, right? So let's see. Looks like 79.90. 79.90 grams per mole of bromine. Right? So I just need to, moles cancel. This is going to be grams of bromine. And that grams of bromine that we're calculating was over here to begin with. Let's see. So 7.99. 9.9. So that's 1.999 grams of bromine over here. Roughly 2 grams. Okay. So if out of this 2.8 grams, 2 grams of it is bromine, how much is oxygen? .8 grams of oxygen, right? Now, how many moles does that represent? $16. Right? So 0.8 divided by 16 is 5 times 10 to the minus 2 moles of oxygen. Okay, now we have a ratio, right? This many moles ended up over here. That many moles of bromine over here. But that many moles of bromine came from over here. So we know that the ratio of bromine to oxygen is, well, they're both 10 to the minus 2. So I guess I should say bromine is 2.50 times 10 to the minus 2 moles to every oxygen 5 times 10 to the minus 2 moles. Okay. So then we can reduce this, right? 10 to the minus 2 disappears. Same for both of them. So it's 2.5 to 5, but the empirical formula needs to be whole number, doesn't it? So what's the simplest whole number? Let me rewrite this. 2.5 to oxygen's 5. So what's the simplest? Right. If this is 1, then that's 2. So it's bromine 2. That's the simplest whole number ratio of bromine to oxygen. in this compound. That's a lot of work for a little answer, isn't it? Really. I think that's why it's important for when you're studying chemistry, you can't just read the chapter and memorize facts. That's why you need to work lots of problems, right? Because they approach from different directions. They're all related in the fundamentals, but to get a grasp of those fundamentals, you need to approach from lots of different directions. That's why I don't know if I told you guys that, but I always tell my New River students, if you're not bored stiff working chemistry problems, you're not working enough of them. And of course, that depends on your time and other things that you have to do. But as many as you can work is better. Okay, that was 29.
Go ahead and talk through 28 real fast.
28? That's 28. Okay, let me back up here. Put it in reverse. Suppose you're given the percent by mass of elements in a compound and you wish to determine the empirical formula. Which of the following is true? Oh, okay. I didn't put that discussion in the work problems, did I? It's not in there. So this would be a good one to do. Okay. So this is 28. Is that even showing up? It looks awful light. Yeah, that's really light. Let me find something a little darker. Maybe the black will work. It's starting to peter out on me too. Maybe it'll stay dark long enough. Okay. You're given percent by mass of elements in a compound. So you're given, that's not going to work here. It's starting to crap out. You're given percent by mass of elements in a compound. Okay. And your target is the empirical formula. What you're looking for. Which of the following are true? Okay. A says you must convert percent by mass to relative numbers of atoms. Okay. You have to take percent X, Y, and Z, there are three of them, to relative numbers of atoms. Is that true? It is. And you look at the empirical formula. In this case, I said X, Y, and Z. So we say X, Y, and Z in the compound, and then you have this many, and M, or what else can I use? NMO. You have a certain number of each in the compound. So that's what we're saying here, the relative numbers of atoms in the compound. That's true. About B, must assume exactly 100 grams of compound. Must assume 100 grams of compound. Does it have to be 100 grams? Here's the key word. It has to be 100 grams? No, it doesn't. It could be anything. Because if you assume a certain amount of the compound, then the percent by mass is going to take that into account when you do the calculation. Right? So they're all relative amounts. So it doesn't matter what you start with. It just is more convenient to use 100 grams because percent means parts per 100, and then the calculation is easy. Right? So if you have something that's 27%, 27 parts per 100, if you have 100 grams, then you got 27 grams of that element. So this is false. You don't have to have 100 grams of compound. It's convenient, but it's not necessary. You must divide all the percent by mass numbers. Must divide all percent by mass numbers by the smallest percent by mass, by the smallest percent by mass. Is that true? When did we actually divide by the smallest number? Was it at the beginning where we had mass percent? No. You got to find moles first. Right? You have mass by mass, your percent, then you convert to mass, then you convert the mass to moles, then you start reducing the ratio to whole numbers. So this should be must divide, well, actually you don't have to. It's just convenient. Divide the number of moles of the smallest one into everything. And that makes the first one, the smallest one is 1, and the rest of them are some other numbers. Right? So this is false on 2 levels. Must divide, no, you don't have to divide. It's just convenient. And percent by mass, you don't divide the mass first. You got to find out the number of moles because this is represented by numbers of atoms, not masses of atoms. Right? You don't ratio them until you get the mole ratio of each of the elements. So this one's false. Where are we? 28D. D. You cannot solve for the empirical formula without the molar mass. Cannot solve empirical formula without molar mass. Is that true? Think of the steps that we go through. When you have percent mass of all your elements, what can you get from that? You can get the empirical formula, right? And that's what we're heading for. So you don't need the molar mass to get the empirical formula. All you need is mass percent. What's this good for? The molar mass, the actual molar mass. That's the next step beyond empirical. If you want to get the the molecular formula, you do need this, but not for this one. To find that one, this is all you need. You don't need that. That's a second step. And then E, at least 2 of the above are true. Nope, sorry, only one of them is true. Okay. So in order to answer those questions, we really just had to think back through the procedure. We're finding empirical formula. Anything else jump out at you? In chapter 3. We can go to chapter 4. Let's see. We actually balanced equations in this chapter, didn't we? Are they giving you any trouble balancing equations? Good. Does that budgeting thing help any? You know what I mean?
The table.
Yeah, where you write it out and then you put the.
Oh, yeah.
Yeah, okay. Might have to dig for another. Those things do not cooperate. There's a red. I wonder if it'll show up. Yeah, sort of. Kind of, sort of. I think the dark ones are better, though. Oh, there's my blue. Anybody's tried to text me. Let me see. Ah, Anthony. What's going on? Where is he? Here he is. No, it's not him. Here it is. Oh, okay. Anthony's going to be here for the lab, but he can't make it to class. Okay. Let's see. Don't need that. Don't need that. Don't need that. Find another one. What about? We didn't have time during class to do any with that use some of those tricks, did we? Except for the polyatomic ions. We did one that had those in it.
52. It has one of the
Okay. For the reaction, what mass P4O10 must be consumed if so many molecules of water are also consumed? Okay. You do that one. 52. And we're starting off. Oh, they balanced it for us, didn't they? That's nice of them. P4O10. That's a solid. Plus this many waters. H3PO4. Okay. Let's name them. What's the name of this one? First of all, is it a 1, 2, or 3 type? Where does phosphorus and oxygen come from on the periodic table? They're both non-metals. Yeah. So we just have to say how many, right? So we say tetraphosphorus, decoxide. That's it. Everybody knows water. Dihydrogen monoxide. Okay. This one, though, it's an aqueous solution of something, and see that hydrogen makes it an acid. Okay. So we say This has got oxygen in it, so we don't start with hydro. We look at the polyatomic ion, phosphate, and 8s become X, phosphoric acid. Okay. Okay, back to the problem. We're going to consume this many molecules of water. Okay? And the question is, what mass of P4O10 is required? So we're looking at a stoichiometric ratio. Exactly how much of this is required to react with this. Okay? So we need some kind of conversion factor, don't we? Right? You have two approaches. You can either convert this, since if we're going to find out what mass here, we've got to use molar mass, grams and moles, right? So eventually we're going to need to know how many moles is that, right? So you can either convert this to molecules of that and then to moles, or you can convert this to moles and then convert that to moles of this. Either way. Let's do moles first. 3.71 times 10 to the 23rd molecules is how many moles of water? So we've got molecules on the bottom, right? Top, bottom, cancel. Moles on the top. What's the conversion? 1 mole equals how many molecules? Times 10 to the 23rd molecules. Okay, so we should divide this into that, and that gives us the number of moles of water. Let's see, 3.71 exponent 23. Okay, divide by this. Did I write that correctly? 371 times 10 to the 23rd. Okay, just check it. And then divide. We get 0.6161 moles of water. Okay. Now we need another conversion factor. Because what we really want is moles of P4O10. So where do we get that conversion factor? Right, we need moles of water on the bottom and moles of P4O10 on the top. Right? That's our answer. We're going to cancel this one. So what's the ratio of moles of P4O10 and water? Every balanced equation has conversion factors in it. They're all related by coefficients.
Oh, okay.
Right?
So 6 moles of water and 1 mole.
Right. So we just divide 6 into that answer. And we get 0.1027. 0.1027 moles of this. Now we just have to convert to grams, right? Of P4O10. We need a molar mass, right? So for every mole, how many grams of P4O10 do we have? And let's see, we're going to have to do some calculating. 30.97 for P. So it's 4 times 30.97, and then 10 times 16 for oxygen. Right? So that's 160 for oxygen and 30.97. So I get 283.88 grams per mole for P4O10. Moles cancel. Leaves us with grams. Let's see if it's still in here so I don't have to type it in again. Close enough. So just times that. 29.1. 3 places. So 29.4 grams of P4. Now let's see, did I get it right? 52. 29.1. Always good to know. Sometimes I do that and get a different answer. Then I have to say, ooh, am I wrong or is the key wrong? Did you follow? Good. Now, that's the first question. Did you follow? Second question is, presented with that type of problem, can you do it? The basic principles still operate. You got a balanced equation, you're given the balanced equation, right? So you can't go anywhere in that equation unless you have numbers. Right? So we could have gone over here with molecules, right? We could have gone from there to there with a 6-to-1 conversion, but eventually you're going to have to make molecules into moles, because in order to have grams, you need a molar mass, and that means grams per mole. So eventually you would have to convert this to moles, whether you did this first or that first. So the principle is balance the equation, check to see if you've got moles or molecules, numbers, before you can move anywhere in the equation, and then you're good to go.
Say, like, just for an example, number 54, it's the same kind of problem, but it gives you mass instead of molecules, but it still be pretty much the same thing where you have to find the.
That one's a little more complicated. We better do that one. Yeah, similar concept, yes. But this one adds what? Whenever you see a problem, a stoichiometric problem, where absolute amounts of 2 reactants are given, one of them is going to be limiting. It's rare that you'll be given a problem where they're exactly stoichiometric. It happens, but I wouldn't count on it. You can expect, in this problem, which was what, 54? Yeah, 54. In this problem, one of those reactants is going to be limiting. So this is a good opportunity to work one of those out. Okay. So we're given the balanced equation. That was nice of them. 4, taken twice, plus 3, H2SO4, sulfate, it's an acid, H becomes sulfuric acid. This is a type 1 compound. Calcium is from the second family, so it's just calcium phosphate. That's it. Yields calcium sulfate, actually 3, here, plus 2 phosphoric acid. And the phases are not given. It's not essential to work the problem. In the problem itself, you're told, you're asked how much phosphoric acid is produced. So this has to be aqueous to be phosphoric acid. Okay, now that's the balanced equation. What are we given? 153 grams of this one. Okay, and we're going to react that with 76.8 grams of that one. Okay? Since we're given absolute amounts of both, one of them has to run out. Oh, it's very likely that one runs out. how much phosphoric acid is produced. So this is our, how much mass of that is produced. Okay, so how do we get there? Remember, we can't go anywhere unless we're moles. So we got to convert this one to moles and that one to moles. So we need calcium phosphate, molar mass, right? 3 calciums. That's like 40 something. 40, is that an 8? Yeah, 4008. And then how many phosphoruses do we have in this? We have 2, don't we? I need to get something I don't have to squint for. There it is. That's what I was looking for. 30.97 for phosphorus. All right, so this is our calciums, this is our phosphorus. How many oxygens do we have? 8 times 16. Add them together. And we can get a molar mass for calcium phosphate. 2 times 37, and then 8, 16. So I get 310.18, 310.18 grams per mole. So now we can convert this to moles. Grams on the bottom, moles on the top. So grams cancel. That means this has to go in the bottom. There we go. If we divide that, we get 0.493 moles of calcium phosphate. Okay. Now we need to do sulfuric acid. So 2 hydrogens, 1.01, and 1 sulfur. Sulfur is 3206. Okay, and 4 oxygens. Oops. Place. Right, then we can add these together. So I need 2.02, 32.06, and 4 times 16 is 64. We get 98.08. This is the molar mass of sulfuric acid. So now we can convert sulfuric acid to moles, 98.08. We'll divide that into 76.8. I get 0.783. 0.783 moles. Okay, so we got this many moles of calcium phosphate and this many moles of sulfuric acid. Now, how do we figure out which one runs out? Since we're looking for this one as our answer, the best approach is to say, what if we were able to convert all of this and there was plenty of sulfuric acid? What would we get? So we convert this, moles of calcium phosphate, to moles of phosphoric acid, H3PO4, and this is calcium phosphate. What's the ratio of those two? Coefficients, right? So we have 2 here, 1 there. So this is going to be 2 times that, 0.987. 0.987 moles of H3PO4. And this is if all of the calcium phosphate is converted. Now we look at sulfuric acid. What if all of the sulfuric acid is converted? 0.783 moles of sulfuric acid. We want to convert that into H4 to H3PO. So the ratio there is 3 sulfurics to 2 phosphorics. So we take this one times 2 divided by 3, 2/3 of it. 0.522. 0.522 moles. These cancel. H3PO4. So, if all of this is used up, we get a half a mole. All this is used up, we get almost a mole. So, which one runs out first? That one. This is our limiting reactant because it produces the least amount of product. And this is excess. So now that we know which one runs out, once this is all used up, the reaction stops. Right? So this is the one that gives us the answer. We know we have this many moles of H3PO4. Now that we know that this is the right one, all we have to do, I might have to move it down here, is convert that to grams. So we need phosphoric acid molar mass, right? So 3 times hydrogen and 1 phosphorus, get 3206. No, 3097. 3097. I'm thinking sulfur. 3097. And then 4 oxygens. So that's a molar mass of our H3PO4. And that's 98.00 grams per mole. Now, this is 98 grams per mole times that value is 51.2. 51.2 grams of H3PO4. Okay? Let's see if that came close to the right answer. 54. We'll go back. Find the problem. Where am I? Look up here. Close, close, close. 51.1. Yeah, it's close. Rounding error. I got 51.2. But that's how you work a limiting reactant problem. Okay? You just assume that all of it is used up, and you calculate what product you get. Assume all of this is used up, and you compare the two. And the least one was derived from the limiting reactant. It's going to run out first. Okay? So, the moral of this story is you have to be very methodical. And you have to know how to do these calculations without thinking about them. Like, because we had to do molar masses for 1, 2, 3 different compounds. So you just have to, this should be second nature to you. And the meat of the problem is in here. How do you find the limiting reactant? That's the one, that's what this problem is about. Okay. That was 54.
Let's do 57. That's the percent yield, and then after that, we'll do the chapter.
Okay. 57. Let's see what that one has to say. There it is. Consider the fermentation reaction of glucose. Okay. This is the moonshiner's equation. You need a fermentable sugar, in this case glucose, and get the yeast working on it, and it'll produce ethanol and lots of carbon dioxide. So you probably, if you know any moonshiners, they never seal that mash container. It's always got a vent. Otherwise it'll explode. Okay, so this is the controlling reaction. C6H12O6 is glucose, and the fermentation gives you 2 ethanol and 2 CO2, carbon dioxide. Okay, so a 1 mole sample of this was placed in a vat with 100 grams of yeast. I don't think that matters, 100 grams of yeast. Uh, 32.3 grams of C250H, C2H50H, 32.3 grams was obtained. 32.3 grams was obtained. What was the percent yield? Okay. The assumption here is that this is probably less than 100% yield. But you need to remember the calculation. What is percent yield? Equals the mass, actual, which is this one. That's actually what we got. Divided by the mass, theoretical, times 100. Okay? So we've already got this one. That's given to us. We just need to calculate what's the theoretical mass of C2H50H. And the reason that these two these H's are separated is based on the structure of the molecule. Right. So this one sits out here. And then the other hydrogens are back here. Right. 2, 4, 6, 5, and then this OH. That's the reason the molecules are written that way. Okay. So we need to find out what's the theoretical mass, right? So if this is the actual amount of glucose that you put in, we should be able to calculate the stoichiometric amount of C2H50H, the theoretical amount, right? If this is 1 mole, how many moles of this do you get? 1 to 2? 2 moles of ethanol. That's how I abbreviate ethanol, ETOH. So we can convert that 2 moles to mass. All we need is the molar mass, right? So let's see, we get 2 carbons, right? And we've got how many hydrogens? 6. There. And we have 1 oxygen. So just add those together. So 2402, this one, 6.06, that one, and 16. 4608 is the molar mass of ethanol, 46.08. And then that gives us times 2, 92.2 grams. This is the theoretical amount of ethanol. And that's the actual amount. So now all we have to do is just plug it into the formula. 32.3 grams divided by 92.2 times 100. So I get 35, roughly 35%. Now, does that come anywhere near the answer? 35.1. All right, so there's a rounding error because I didn't get 0.1. Maybe if I had not, I don't know. I always pick the best answer, even if it's not exactly what's on the multiple choice. And then if I count it wrong, you can argue. That's a student's right, isn't it? Argue for points. Are we okay? Yep. You just have to go back to, I mean, the question was, what's the percent yield? Well, you got a definition, right? So you just put that up there and say, all right, what do I know? I mean, what's given to me already? That's given already. I just need to find this. And what they say in English, Bob's your uncle. I don't know where that came from. I take it to mean it's a done deal. Okay. Oh, we're ready for, let's see. Let me see if there's anything else in here that needs to be dealt with. Are you good with balancing combustions? Let me see. I saw one over here a minute ago. Combustion. We take a hydrocarbon. Where is it? That's not it. That's not it. I could just make one up. I thought I saw one. C2H6, I think it was. Combustion. C6H14.
Yeah.
43. Right. Did you get that one okay? I mean, were you good?
I didn't even try to do that one. I did the ones above.
Okay.
I did like 39, 40.
Okay. Let's do this one because there's a trick involved in this one. C6H14 plus oxygen, and I'll leave myself a gap here. Coefficient there.
Like 1 second. My mom's calling. I gotta
Okay.
make sure this.
Okay, that's fine. We shall pause for a second. Here we go. Okay, let's just take a few minutes. We won't spend a whole lot of time because we haven't even gotten in chapter 4 yet, and we've only got 40 minutes. Okay, so we're going to just do our budget: carbon, hydrogen, oxygen. So we have 6 carbons here, 14 hydrogens, 2 oxygens. On this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Whenever you've got an odd and an even in your mix like that, look out, because it can be trouble. Okay, so I'm just going to start with carbon. So if we put 6 carbons over here, okay, that makes 13 oxygens. Okay, Now, oh, by the way, we've got an element over here by itself. We're going to leave that one to last. That's one of the other tricks. We don't want to put anything in front of this one until we have to, at the very end. So hydrogens. If we got 14 hydrogens over here, and we want 14 hydrogens over here, that means we need 7, right? 7 times 14. So that gives us 14 hydrogens. But it also gives us 7 oxygens plus 2 times 12. 7 to 12 is 19, right? 19 oxygens? Yeah, 19. So now we have 19 oxygens over here. Okay? Now what do? The only place you can go now is to oxygen. But you can't multiply oxygen by any whole number because there's a subscript of 2. So any number you multiply times oxygen is going to be an even number, right? 2 times any number is even. And that's odd. So here's what you do. You multiply it by a fraction. "19 halves of an O2 is 19. Right? If we were to take 19 of it, it'd be 38. But 19 halves of it is 19. So now we got 19. And technically it's balanced. But we want to convert it to whole numbers. Right? So you got to get rid of that fraction. All you got to do is multiply the entire equation through by the same number. So we're going to multiply through by 2. Right? Let's see this. By 2. So 2 times 1 is 2. 2 times this gets rid of that 2. 2 times this is 12. 2 times this is 14. And we used our 2. So now the coefficients are 2, 19, 12, and 14. And what was the question? 43. The sum of the coefficients. Okay? He wants to know the sum. So you just take 2, 19, 12, 14. That's 6, 15, 17, all right, 17, and 47. So that's why the answer is B. Okay? So that one actually had 2 tricks in it. Holding this one to last and using a fraction. Okay, now we can go to chapter 4. Chapter, let's see. Chapter 4. Did you take a look at these things in chapter 3? Remember, the empirical formula is the simplest whole number ratio. So if you've got, the first one is how many carbons? 1, 2, 3, 4, 5, 6. And 6 hydrogens. So the molecular formula for that one is C6H6. But the empirical formula, CH, right? So use that reasoning for the rest of them and you'll be fine. Okay. We're ready for chapter 4. Which one do you want to tackle? Chapter 4. What do you think of number 4? All the following are weak acids except. Do you remember the list of strong acids that we had? Give you the strong acids. I think this is number 4. The strong acids included things like this one, this one, this one, or this one. Well, it turns out that the same family of chlorine, bromine, right, is also a strong acid, right? But here's the kicker. In that same family, you can have HF. And HF is actually a weak acid. Right? So it's counterintuitive. You would think that being in that same family with bromine and chlorine, that HF would be a strong acid, but it's not. It's a weak acid. It does not dissociate very much. Right? In solution, they have to make those to be an acid, right? And it doesn't make very much of that. But these two, they completely dissociate. They're strong. That one's weak. Now, explaining why is another issue.
Just memorize it.
Yeah, for now. We'll eventually, well, I don't know. We'll get to it or not. Let me see, in this course. Let me look at the topics just to get a refresher.
Go ahead and do number 5 while you're at it.
Okay. Atomic structure period. This
76.
Yeah, we probably won't get to that then. Okay, number 5. That information could be in your textbook. So number 5, which of the following is not a strong base? Okay, so we have this one, A, B, K, O, H, C, N, H, 3, G, lithium hydroxide, and E, strontium hydroxide. Okay, you can do this by process of elimination. If you make a hydroxide out of each of these, it's strong. What do we mean by strong? It means it completely dissociates. When it goes into solution, it just breaks apart completely and makes, in this case, calcium plus 2 hydroxyls in solution. Right? KOH is, this is in the second family, same thing. First and second, alkali metals and alkaline earths will make strong bases. So this one does, this one does. Lithium, all right, it's an alkali metal. Strontium, an alkaline earth. They all, these guys, are strong. So by process of elimination, we've got ammonia left over, okay, as our weak base. But notice that ammonia doesn't have an OH in it. Right? So how do you get an OH out of that? It reacts, when you put it in solution, it reacts with water and makes, then it dissociates. But the thing about it is, now I'm going to use a double arrow here just to make a point. It prefers this, right? Once it makes this, it likes to stay there. Actually, you know, to be honest with you, it prefers to be this, dissolved in water. It doesn't even make that. Right? So that makes it a weak base because it produces very little of this. Now, we're talking in chemical terms. Whatever goes into solution completely dissociates for these guys. But for some of them, a lot of it doesn't go into solution. But the definition of a strong base is whatever goes into solution completely breaks apart. So we're not talking about, is it strong enough to eat your skin? Chemically speaking, it's strong because it dissociates. Right? So calcium hydroxide and strontium hydroxide are only slightly soluble in water. But when they get in water, they break apart. Okay? But this one is a weak base because it does not produce a lot of hydroxyl, no matter how much is in the solution. Now you can, if you manage to saturate the solution, you can produce enough hydroxyls in absolute terms to eat your skin. But in chemical terms, this guy's weak and the rest are strong. Okay, what's next?
Just to jump up on that, number 8.
Number 8. Okay.
But in the first one, because they are dissociating it, that's stronger acid, right?
Okay, for those, right, for those two, you have two choices. You have lots of these individual, and none of them are molecular. And that's Roman numeral 1. Roman numeral 2, you do have some that remain together. Okay. So in that case, I would classify this as weak and this as strong. Okay. But to answer the questions, in case 1, HX is acting like a weak acid. No, it's not. It's acting like a strong acid. Right, so that was false. B, in case 1, HX is acting like a strong acid, and in case 2, HX acting like a weak acid. Yes, that's true. So B is a possibility. In both cases, HX is acting like a strong acid, false. Both cases acting like a weak acid, false. Right? It's one and the other. Strong, weak. So HX is not soluble in water. Well, that's false, because you can see it's right there. So the only one that answers that is B. Yeah, some of these that have those diagrams, kind of hard to interpret if you haven't seen them before. How we do it?
Let's look at number 10.
10, okay. Are we covering everything that?
Yeah, that's what I'm
Did you-
Yeah. Yeah, I'm circle number 10 too.
You're good? Okay. 10. All right. Let's see, what are we given? 1 ml of 3.5 times 10 to the minus 4th molar solution of oleic acid is diluted with 9 milliliters of petroleum ether, forming solution A. Then 2 milliliters of solution A is diluted with 8 milliliters of petroleum ether, forming solution B. What's the concentration of B? Okay, we're doing a serial dilution. That's what that is. So we're given, to begin with, the molarity of our oleic acid is 3.5 times 10 to the minus 4th molar. And out of this, we're going to take 1 milliliter and add 9 milliliters of petroleum ether. Petroleum ether is an organic solvent, right? And you need an organic solvent for oleic acid. It's insoluble in water, right? So that's why you need petroleum ether. Petroleum ether is really a fraction of distillate. Right? So it's a combination of things. It's not really ether. Okay? It's a misnomer. Chemically speaking, it's not ether. But here's what we have to assume. We have to assume that when we put 1 milliliter of this together with 9 milliliters of that, the total volume now is 10 milliliters. That's our first assumption, right? We're not told that, but you can't work the problem unless you do that. Okay? So, if we're starting out with this, and we're saying M concentrated, volume concentrated, yields M dilute, volume dilute, then we say, okay, we know what this one is, right here, concentrated. So that's 3.5 times 10 to the minus 4th molar. And the volume of the concentrated is 1 milliliter. Right? The molarity of the dilute is unknown. But the final volume of the dilute is 10 milliliters. Okay? So it's important to get these things in the right position before you try to solve it. So now, what does that become? This then is equal to this divided by that. Right? So it's actually this number divided by 10, which is 3.5 times 10 to the minus 5th molar. We diluted it by a factor of 10. So that just changes the exponent from minus 4 to minus 5. Okay? That's the first dilution. Now the second dilution, this is solution A. We're going to take 2 milliliters of solution A and dilute with 8 milliliters of petroleum ether. So now we're going to take 2 milliliters of A and 8 milliliters of petroleum ether. That gives us 10 milliliters. And we want to know what the concentration is. So if we use this same expression, now the concentrated is this one here. Because we're diluting it to something else. And the volume that we took out of it was 2 milliliters, right? Oh, while I'm at it, notice that milliliters on both sides. Okay, so they cancel. This is a ratio. So you don't have to convert it to liters to use this expression because the milliliters are on both sides. They will cancel. Okay, so now the new diluted, so this is diluted A and this is diluted B. We're going to end up with 10 milliliters here. Okay? So now we just solve for that. So it's 2 times this divided by 10. So what's 2 times 3.5? It's 7 times 10 to the minus 5th molar divided by 10. So the new concentration is 7 times 10 to the minus 6 molar, right? Because we're dividing by 10, which reduces this one another 10. 10 to the minus 6. Let's see, that's number 10. It should be, yeah, 7 times 10 to the minus 6. That's what's known as a serial dilution. We use it in chemistry sometimes. It's more common in microbiology, where when you're trying to plate out microbes, and they're really concentrated. So you take a certain amount of suspend them, and then you dilute them, and then you suspend them and some more, and you take some out and dilute them again, and then you just keep doing that. And each time you dilute, you take some of that and pipette it into a petri dish. Right? So you make serial dilutions, and this one's too concentrated. When they grow, it's just a mat. So you look at this one. Oh, starting to show some individual colonies. Okay, let's go down to this one. Ah, here we go. Individual colonies. So we diluted it enough. And in some respects, you can use that dilution to determine a rough estimate of what was the concentration of the original solution. You just work backwards, right? This is a 10 to 1 dilution. This is a 5 to 1 dilution. So 10 times 5 is 50. So overall, we went 50 to 1 dilution from this to that. Okay. But it all revolves around this expression right here. I think my slides were M1V1, M2V2. But this one, I think when we say concentrated dilute, it might be easier to follow. Yeah. Another one? Because we're bumping up against, let's see, we need 3 o'clock. We got 17 minutes. We could probably bleed over into lab a little bit if you want.
You picked what you think is absolutely very.
Okay.
Do you have anything else?
No, I just have other things on this.
Okay.
I didn't make it very far into it.
So you can probably calculate molarity pretty easy, right? You just need number of moles and the volume that you put it in. That's another dilution one. We want to do that. If you need to get a molarity of something, moles per volume, this has to be in liters, that has to be in moles. But your balance doesn't measure in moles, it measures in grams. So it depends on the compound that you're going to put in a solution. Right? So you do need molar mass. And if you do this calculation, you say, okay, I need a certain molarity and I need a certain volume. So those are going to be known. So you would solve for N equals M times V. And if you multiply these two together, that tells you how many moles you need of the compound. Now, once you know the moles of the compound, then you can convert to mass and weigh out that much mass on your balance, then put it in this volume of solution, and you have that concentration. Let's see. Oh, classifying reactions. We didn't spend a lot of time on that.
What number?
Let's see, where do they start? They start about number 26. So these are the reactions in number 26. Okay, that one. This one is cerium 4 plus 2 iodine yields I2 plus 2 Ce plus. And this one, HOAC. What is HOAC? It's an abbreviation for acetic acid. Okay? Plus ammonia yields ammonium plus OAC minus. Okay, so let's see what we got here. What's not given to you is you have to determine for yourself. Recognize that this is a net ionic equation, right? Because there are no counter ions. There's no anion for this one, there's no cation for that one. And then you have to say, what is that? PbI2. You look up on that chart here, lead and iodide, you'll find that this is a solid. Okay? So that means that this is a precipitation reaction.
Well, are we gonna have these available?
Oh, yeah. Yeah. In a review document like this, if there's anything useful information in the back, it will reappear on the exam.
Okay.
Yeah, so just learn how to use it. Let's see, where was I? The next one. Okay, for this one, what we have is cerium 4 plus becomes cerium 3 plus. Right? So for this one, it gained 1 electron per cerium. And for this one, it went from -1 to 0 oxidation state. So that means loss 1 electron per iodine. Okay. That's as far as you have to go to identify the equation. We don't have to balance it. But what it tells you is that you had a gain and a loss of electrons, which means redox. Okay. For this one is a little trickier. This is an acid, we know that. And from our previous question, this is a base. So what we've done is we've transferred this hydrogen to that ammonium and made ammonium ion and acetate ion. This is an acid-base reaction. So now that we know what we're dealing with, let's look down at the A, B, C, D, E, and see which one fits. A, acid-base reactions. Well, one of them is, but not all of them. Unbalanced reactions? No, I think they're balanced. Right? 1, 2, 2, 2, 2, 2 here, 2 there. 1 hydrogen just transferred over. So they're all balanced, so B can't be it. C, precipitation, yes. Acid base, yes. And redox, respectively, no. It's precipitation, redox, acid base, respectively. So that makes it E, right, in that order.
So for the acid-base reactions, pretty much that's usually recognized that there's an acid and a base.
Are you talking about the
Or the react.
A question? Is that what you're talking about?
No, I'm just saying in general.
Oh. Just saying. Okay. Question again?
To recognize that it's an acid-base reaction, just recognize that if there's an acid and a base as the reactants.
Yes. And then, of course, in any acid-base reaction, a proton is transferred. So this proton goes over here, right? Becomes that, and we lose it, and it becomes that. see. I want to be sure I'm not missing something. Okay. So I suggest that you go through the rest of these and look at, let me be sure if I've got them done. I don't want to tell you something that's wrong. So 27, say 27, 25, 6, 7. Yeah, they're there. Right. So there are descriptions in the worked problems of the rest of these types that will tell you what they are. Okay. The only reason I'm not going through all of them is because we don't have time. And I think there's something else that's important we need to get to that we didn't spend a lot of time on the last time. And that is writing complete molecular equation, complete ionic and net ionic. So let's look at one. Let's see if we can find one. Let's see. Do we have any fill in the blanks in the back? Completion questions. We do. Okay. Let's take. Where is it? I don't want that one. Oh, I thought there was another one back there. Well, oxidation states. Rules for oxidation states. Remember those? I may not get them in the right order, but we'll get them all up here. How to calculate, in order to calculate an oxidation state, which is not necessarily a charge, but it's a way of bookkeeping our electrons so we know whether they've moved. So if you have a one elements, and they can be diatomic or polyatomic elements, but if they're elements, then the oxidation state could go here. Oxidation state for all elements is 0. Okay. This is elements not charged. Simple ions, like a single element that is assumed a charge. The oxidation state is the charge number. Right? So if we had sodium chloride, sodium would be +1, chlorine would be -1. So the oxidation state for sodium would be +1, for chlorine to be -1. Okay. Oxidation state for elements in compounds equals the charge on the element, charge number on the element. So that being said, you have type 1, type 2, and type 3s. Well, the only ones that matter for this one are the type 1s and 2s. So the type 1s are fixed charge. So anything that comes from alkali metals, alkaline earths, halogens will be the fixed charge. Right. Then we have oxygen in a compound is -2. Unless it's a peroxide, and then it's -1. But in most cases, it's -2. Actually, fluorine in a compound is -1. And chlorine and bromine and iodine, they can vary. Right? So you don't give them a fixed charge unless you have to. I know I'm missing something. Oh. Total oxidation state of a compound is 0 because the compound is neutral. So all the oxidation states have to add up to 0 in a compound. And then polyatomic ion the total has to add up to the charge on the ion. Okay? With those rules, we should be able to calculate variable oxidation states on any of our other elements. Okay? So why did I go to all that trouble? Well, when you start balancing equations, it helps to know where the electrons are headed. For instance, let's do this. This one's simple, 63. We have this one plus this one equals this one and plus this one. Okay? Oxidation state on this one. It's an element. It's 0. Oxidation state on this one. It's an element. 0. Oxidation state on these two. That one's -1. That one's 3+. Okay? So now, where do the electrons go? For the iron, you went from 0 to 3+, which means you didn't gain 3 protons, you had to lose 3 electrons, right? To give you that 3+ excess. So there was a loss of 3 electrons per iron. So for every loss, there has to be a gain. This bromine went from 0 to -1. That means we had to gain 1 electron per bromine. Okay. So let's say that the number of electrons transferred has to balance. So if we hold this one constant at 3, and we say this one is going to be made up to 3, how do we get 3 electrons out of that? Well, it's 1 electron per bromine. So if we just make 3 times this, that doesn't work because we've got 2 here, 3 there. That's not a balance. So what if we say, if we say 6 here and 3 here. So that's 6 bromines, 6 electrons. Okay? Dilution. Okay, now that we've got 6 electrons here, we've got to have 6 electrons here. So how do we do that? We really only need to multiply it by 2. That means 2 here and 2 here. And then you can check 2 irons, 2 irons, 6 bromine, 6 bromines, and the electrons balance. Okay. So let's, yeah, it's 3 o'clock.
So which,
Yep.
would you do the coefficient of the end part? It asks which coefficient.
This one?
Yeah.
Okay.
I mean, it just asks,
How did I get to that part?
no, it says in the balanced equation, the coefficient of, oh, never mind, the B or minus, never mind.
It's 6.
I had a pencil over that.
Okay. All right. Now, this is a redox method for balancing equations. I'm not sure if we're going to get to it in this class. I think we do. Hold on a second. Geometry. No. Okay. We wouldn't get it. We wouldn't get the half reaction method until second semester. And in that case, we break this apart into 2 reactions. We have the oxidation reaction, the reduction reaction, balance them, then do any adjustments so that they can add back together. And that actually works better than this. And it also allows you, with the half reaction method, sometimes you have to add acid in, you have to add water in, sometimes you have to convert it to base. So you can do more with the half reaction method. But this is the quick and dirty redox method of balancing. Let's see. Well, we could spend a whole lot more time on this, I guess. But I want you to be able to finish your lab. This is what it's called. Lab techniques. Yeah, lab techniques. So we're going to do measure lengths, we're going to measure masses, we even measure volumes. Oh, we get to play with fire too. Now, if you have a question between now and next time we meet, you can contact me. I mean, if it's not urgent, send me an email through the Southern system. I've got my phone synced to my Southern email, so I'll get it. Or you can send it to my New River email. Either one, it doesn't matter. Or you can text me if you need a quick response. So don't think you're isolated. I'm available. It's back here. We'll go. There's 3 of us today. I guess that's one group. Okay. Now, am I expecting any reports? The lab, yeah. Let's see, I've got extra credit here. This is graphing techniques. Yeah, okay. See your name back here. Or you can do it in bonuses, right? Yeah, we're on the front page. So, if you need to take a break, we'll meet in maybe 5 or so minutes. I'll give you enough time to pull some other things out. I've already got the water started boiling. We have, oh, temperature. Forgot that one. Measure temperature too. Okay. Let's see. Oh, I need to shut this down.